Okay, so let's start the class. I want to go over because for this unit it's mostly conceptual questions, right? You have some math, but the math is quite easy. You see, I want to go back to the magnetic field lines. You see, a magnetic field always curl around. It will never diverge or converge. So it is always going from the north into the south. So I have updated. Those slides are called Big Idea Magnetism. It's in your Dropbox. But you can see here, you can take a compass and you can visualize which way it's going to flow from north into the south. So here, instead, you can have a bar magnet or you can have a little piece of iron, like iron filing. It will get magnetized and it will show you, okay, which way is the south, okay, because this is like a bar magnet that will be the north and that will be the south. So north wants to go to south and south wants to go to north. Now, remember, if we have a loop of current, okay, so if you have a loop here, okay, it's a coil, and you have a wire going around and around and around, and then it's connected to a power supply. You take your right hand, okay, you go along the current, so the current is flowing this way, you do this, okay, and what you get here is that the loop of current will behave like a bar magnet. You see, your thumb here will show the north. Okay, so a loop of current will behave like a bar magnet. Okay, so the current is flowing this way. So that will be your north and that will be your south. Is that clear? I want to stress that out to make sure that it's clear for conceptual question for test number 3. It's going to be a lot of conceptual question. So again, this is my loop of current. I don't know if I can zoom out. If the current is going this way, you see my thumb will show you the north. Okay? So if you have a magnetic field going from left to right, can you see that? From left, magnetic field going from left to right. Okay? The loop of current will be acted upon by magnetic field. So you're going to have a torque, a twist, and the loop will twist in such a way that it wants to align with the magnetic field. So if the magnetic field goes from here, from the left to the right, the loop will rotate, will twist. Okay, so it will be acted upon by a torque. A torque is a physical quantity to measure how much twist is happening. It will align itself. It's going to be very important for what's coming. Do you understand? So a loop of current behave like a bar magnet. Okay? So the current is flowing in this direction. The thumb is the north, and here is the south. So if you have a magnetic field going this way, from the top to the bottom, and you have a loop here, a loop of current, okay, it will rotate to show which way the magnetic field is flowing. So it will align itself with the magnetic field. Do you understand? So very important for conceptual. Okay, so we have cookies today to celebrate. It's vegan, no seed oil, no preservative. It's halal, it's kosher, it's vegan, whatever you want it to be. It's not keto. So it's not low carb. But I think keto, you can have up to 50 grams or 20 grams. So it's less than 20 grams per cookie. So if you are keto, it should be okay. So anyway, let's go back to our business. The earth here, everything happens like it's behaving like a bar magnet. And again, you can have all those little bar magnets here, compass. If you have a compass here, it will show you which way it's flowing. So you have an assignment. You see here at the equator, how is the magnetic field here relative to the ground? Relative to the ground. So if you're at the equator here, see the magnetic field of the Earth is perpendicular or parallel? Parallel, very good. And if you go high up here, increase the altitude, you see it's going to make an angle there. Right? You see how it works? Now, if it's there at the pole, then the magnetic field is what? Parallel or perpendicular? Perpendicular. Okay? So we're going to talk about that today. You see, if you have a loop of current, again, if you have a loop of current, okay, everything happens like you have a bar magnet. If you have this loop inside the magnetic field, okay, it will be acted upon by a torque. It will twist in such a way that it will align itself with the magnetic field. Do you understand? So that will means it's at a lower potential energy. If you do whoa, yeah, see, imagine that. Imagine you have a magnetic field coming from the bottom to the top. Right? So bottom to the top, the loop wants to be this way, right? If I want to flip it, if I want to rotate it, okay, I need to do what? Yeah. And now it's at a high potential energy level, right? And then it wants to go back where it was before. Okay? It's going to be important if you want to understand MRI, for example. So we'll talk about that. So that was the first thing I wanted to emphasize. So if you came late, there is cookies and you have to go over the first part of the class. Here, okay, I want to go back to that right hand rules because it's applying, but for different situation. First situation that we have seen, if you have a wire, okay, so if you have a current carrying wire or a wire carrying current, I don't know how you say it. So if you have a wire with a current flowing, the thumb will be the current. And you see the magnetic field is going to circulate around the current, right? Okay, so that was the first time we used the right hand. You can see the same thing here. If the current is flowing to the right, then the magnetic field will circulate around. Okay, so that was the experiment by Oersted. So if you put a little compass here, it will be perpendicular to the wire. Okay, that was his experiment. Close to the wire, the magnetic field is going to be strong. As you move away, it's going to be weaker. Okay, so make sure you go over that. We did that last lecture. Now, if you take a coil, okay, so if you take a wire and you go around and around and around and around and around and around, connected to a power supply, what we get, it's called a solenoid. A solenoid will behave, or a loop of current. So it will also behave, it's going to be an electromagnet. Okay, you make an electromagnet and it will behave like a bar magnet. To find out which way is the north and the south, again, you use your right hand, but not the same way. Now, your palm here, that hand here, will be the current flowing. Okay, so if the current is flowing this way, okay, so it's doing this, okay, then the north pole will be that top here, and that will be the south pole. Do you understand? So it's not the same. We are not using it for the same way. Here the thumb is the current, and your palm was the magnetic field circulating around the wire. So here you have a straight wire. Now if you take that same wire and you make it in a cylindrical shape, so then you take your hand here and you go around your loop. Where is my loop? Around your loop like this. That will behave like a bar magnet. That will be the north and that will be the south. Okay, that will be the second way we use our hand, right hand. If you are a lefty, you can use your left hand, but then at the end you have to reverse everything. Here you have one loop of current again. going this way. Here will be the north and here will be the south. Yes? Okay. And then you can use your right hand again in a third situation, in a different situation, where you have a current, okay? So a wire with current flowing through it inside a magnetic field. That wire will be acted upon by a force, okay? And you can use your 3 fingers. I like to use this. You can use that. Yeah, there are different way to use it. But if you use this one, again, you say IBF. IBF. So if this is the current, if this is the magnetic field, that will be the deflecting force. The force is perpendicular to both the current and the magnetic field. Is that clear? Now, the magnitude of the force will be the current flowing through the wire, the length of the wire inside your magnetic field, times the magnetic field, times the sine of the angle between I and B. Okay? So what's going to happen if the angle equals to 0? So it means the current is parallel to the field. We're going to get 0. Very good. Okay? If the current is parallel to the field, there is no force. If it's anti-parallel, there is no force. Okay? So again, if you have those 3 vectors, let's say this is I and this is B, IB, it's in the same plane, I'm going to have a force here perpendicular to both. That will be the maximum if those are perpendicular to each other. As I decrease the angle between them, you see the force is going to decrease, 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 decrease. When they are parallel, there is no more force. Okay, I can make it the same way. You start from here, so here it's parallel. If they go the other way, so now they are anti-parallel, it's going to decrease, decrease, decrease. Anti-parallel is going to be 0. Is that clear? So you have different way to do it. If you don't like your finger, you just have to be flexible, okay? You just have to be able to do this, to do that. You know, it's like yoga on the hand. I'm gonna launch a new trend, right? To yoga with your hands. So anyway, you can do it this way too. That way works too, okay? That could be I, B, and F will come out of your port. Next, we're going to see that instead of having a current, so what is a current? What it's made of? If you think about Benjamin Franklin, so a current is just moving positive charges, right? So if you have a moving positive charge, instead of having a current, like if you have a proton moving inside the field, it will also be deflected, and we will use the same rule, the same right hand rule. Is that clear? So if you have a proton, for example, or a positive ion moving isotope, like an isotope, but it has been stripped out of 1 or 2 electrons, so it's positively charged, moving inside a magnetic field, okay, it will be acted upon by a force as well. So we will have to massage a little bit and shake a little bit that equation. And what we get at the end, that's what we're going to see today, later today, is that the magnetic force acting on a moving charge will be equals to, in magnitude, the charge, the velocity, which is a vector, the magnetic field, which is a vector, sine the angle between the velocity and B. So that will be the particle moving in this direction, it's positive. That will be the field, and that will be the force. Okay, so if you have a positive charge moving in this direction, and you have a magnetic field going in this direction, it will be deflected. Okay, so what's going to happen? You see that the velocity here will be perpendicular to the force. Remember from physics 1, what's happening if a velocity, like the moon moving around the earth, okay, it wants to go in a straight line at a constant speed, No, you can't. There is gravity pulling the moon toward the Earth. That force here is perpendicular to the velocity. When that happens, you have a circular motion, centripetal force, right? I'm just refreshing. So, by the way, make sure that before any test, and that should be true for any class that you are taking, make sure you look at your equation sheet and you understand the equation and you see through the equation. You really understand the meaning of each equation. Is a physical quantity proportional to the distance? Is it inversely proportional? Is it inversely proportional to the distance squared? What's the meaning of each physical quantity? Okay, and that should be true even for biology or any science that you are taking. You have to look at your equations. You have to make sure that you understand the units and the meaning of the equations. Okay, so that was my talk for today. Again, those who just came, I have cookies, healthy cookies. Healthy, it means no seed oil, no preservative, no, just flour, sugar, and butter. And that's it. It's not low carb. Okay, so let's go back to our business. So test number 3 is scheduled the Tuesday, April 2nd from 8 p.m. to 11 p.m. I will keep reminding you. Okay, so let's go back to our unit. We did this one. Okay, you see that will be the force here, the magnetic force if you have a coil. The force is from that permanent magnet. So we did that last time. Okay, so for example, we can do number 1 together. It's the same type of question. Okay, so you have to take the current here. You have to take the diameter of, not the diameter, the distance around, circumference, times the magnetic field. Okay, so you can do that quickly. By the way, this comes from the book Johnson and Cutnell. So even if you have an old edition, that will be fine. It's hot, isn't it hot? Like, I don't understand. We went from, I don't know, winter to summer like this. Huh? Is that, oh, it's just me. You're not, it's not hot? Oh, it is very hot, right? The weather in Florida is bipolar, okay? It does not know what it wants. Okay, so that will be the magnetic field. Again, look at the unit. So the number of turns here is N. So that means you have N coil. And then you see you're going around here. And so you can find the length of a wire will be 2 pi r. Okay, so we discussed that last time. I'm not going to go over that. So it will be pi times the diameter. So the length of the wire will be pi times, you have to convert to meters, 0.025. Okay. So find the force. So the force is the number of loops, so N times the current times the length. Okay, so each loop has a length of 2 pi r. And each loop is acted upon by a magnetic force because of the permanent magnet, but those forces add up. Okay, so each loop is acted by a force ILB, and then you keep adding them, so that's why you have the number of loops here, times B, and they are perpendicular to each other, so I don't have to worry about the sign. I have B, I have L, I have N. How can I find the current flowing? Ohm's law. Okay, very good. Because it says the Ohm's law. Remember Ohm's law? V equals Ri. And we have the resistance R, we have the voltage, so we can find the current. Do you understand? Okay, so the voltage is 15, the resistance is 8, and the current is I. So the current will be, yeah, who said that? Who's you?
Jack.
Huh? Jazz?
Aggie.
Aggie?
Jack.
Ah, Jackie. Okay, so the force will be, the number of loop is 250 times the current is 1.875 times the length is 2 pi r. 2r is the diameter. So pi times 0.025 times 0.15 is the magnetic field. Okay, so a coil inside the magnet, okay, will be pulled or pushed. Because it's a speaker, so electricity flow in and out, in and out, in and out. So the coil will be pushed and pulled, pushed and pulled, pushed and pulled at the same frequency as the current, which has the same frequency as the sound that you want to produce. So that's how a speaker works. So that will be,
There's no sign thing.
no, because it's perpendicular. Okay, so if you go back to the slide here, we did that last time. You see the magnetic field here is perpendicular to the wire. The wire goes into the screen, and this is B. So that will be F. Okay, so each wire, each loop will be acted by a force. So you add those forces because they are all in the same direction. That's why you multiply by the number of loops. Okay, so the coil here will be pushed and pulled, pushed and pulled, pushed and pulled by the permanent magnet. And the frequency will be the same as the frequency of the current flowing in and out, in and out. So if the current is flowing at a frequency of 440 Hertz, that's going to make a A4. For those who are musicians, A4 is used to tune violin or piano, for example. So it's going to be pushed and pulled by the same frequency, and that's how you're going to make a sound wave. And your eardrum will be pushed and pulled at the same frequency, and that sends a signal to your brain. Okay? So did you all find that? Okay, so let's try to do number 2. Number 2 is easy. It's just a numerical application. And again, you want to read your textbook, okay? I recommend Johnson and Cutnell, but the other one is also good. So you have the current here. You have the length of the wire, which is 0.25 meters. So you identify each physical quantity. So this one will be B. Can be found using the equation, the angle between the wire and B. Okay, so we have different angle here. So you have the I and then B. That will be the angle between them. And that will be the force here. So the force equals B, I, L, and the sign between them. So you can plug it in. So the first one, F, will be equals to 0.85 times the current is, what is the current? 15, thank you, times 0.25. How much is sine 90? 1. Okay, so that will be the maximum force that you can get. Do you all agree? So it's going to be 3.2 Newton. So that's for if the angle is 90 degrees. So if you go back to my big idea here, you see the current is flowing in this direction. That's the segment of the wire inside your magnetic field. The angle is theta, and that's going to be the force. Force is perpendicular to both the current and B. And I lost my thing. Okay, what about the angle is 45 degrees? So you're going to have F equals, so 0.85 times 15 times 0.25 times sine 45. Okay, so you're going to get something smaller. 2.25, so 2.3 Newton. Do you all agree with that? Make sure the mode is in degrees, not in radians. Now, if the angle equals 0, so it means if the current and B are parallel to each other, the force will be equals to 0, because sine of 0 is 0. Do you agree with that? Sine of 0 is 0. If the angle is 180 degrees, that means they are anti-parallel. So the current is in this direction, B is in that direction. Okay, so that means this. If it's 180 degrees, sine of 180 is also 0. So to have a magnetic force, you need an angle between the current and the magnetic field. Or if it is 0, there is nothing. And if it's anti-parallel, there is nothing. You can have an angle of 180, but sine 180 equals 0. Any question? Okay, so I'm going to leave that for the pop quiz. Oh, just to make sure that everyone understands, if you have a vector, okay, you have a tail and a head. If it's in the screen, you're going to see a cross here because you see the cross there. If the vector is towards you, you're going to see a dot, okay, because this is supposed to be pointy here. I don't know if I have like, okay, this is better. Okay, so this is a vector. So if it's in the screen, you're going to see a cross. If it's towards you, you see a dot. Is that clear? Okay, a vector has a tail and a head. Towards you, you see a dot. Into the screen, away from you, you see a cross. So that means the magnetic field is towards you, and the wire is being deflected up. And the question is, will the current going to the right or to the left? Okay, you have a lot of applications, so you have those boat, and the way it works, you can make it work without fuel. I don't know if it's going very fast or not. I don't even know if they do exist. I mean, they exist, but I don't know if it's a prototype or if it's around. I don't think it will go really fast. But anyway, the idea is that underneath here, you're going to have two electrodes, okay? One will be positive and the other one will be negative. So you need a battery inside your boat. So this one positive, this one is negative. So because the water is salty, you're going to have a current flowing here from plus to minus, okay? Because you have like electrolyte inside the salty water. And then underneath here, underneath the boat, you have a permanent magnet. Permanent magnet, so the magnetic field is going this way. Do you agree? So you take your right hand, okay, current is going this way, magnetic field is up, so the force will be there. Okay, so that means there will be a force acting on the water in that direction. So action, reaction, the water will push back the boat in the opposite direction. So it works like a balloon, that you inflate a balloon, you let go, air will go in one direction, the balloon will go in the opposite direction. So it's working with Newton's third law. Okay, and then so again, if you have a loop of current, if you have a loop of current again, you use your right hand here, and it will behave like a bar magnet. Do you agree? Now the quantity here, current times the area, it's called the magnetic moment. I don't know what it says. It is a magnetic dipole, but mu is called the magnetic moment. Okay, but for now you don't have to worry about it. But you have to understand that this little loop here will behave like a bar magnet. Okay, so if you place that little loop inside a magnetic field, it will be acted upon by a torque in such a way that the loop here will align with the magnetic field. Is that clear? If you excite that loop, okay, so there is energy, so it's going to a higher level of energy, so it's going to be not happy, so it will rotate back to its lowest level of energy. And that's how an MRI works. So how does an MRI work? I don't know if I can show you that. In a nutshell, okay? Um, Okay, I'm going to use that. So in the body, you have a lot of hydrogen. Okay, so hydrogen are like protons, and those little protons, okay, that are hydrogen atom is made of a proton and one electron. Do you agree? So those nuclei, so those protons, they actually spin. So because they spin like a top, they will behave like a current loop, a loop of current, right? So those little top will behave like a small magnet. That will be the north and that will be the south. So each hydrogen atom, and we have them especially in the soft tissue, not so much in the bones. You know better than me because you're good at anatomy. All those soft tissues that we have inside us, it's full of hydrogen atom, and the hydrogen atom will behave like a loop of current, right? Because they spin. So it's like a spinning top. So that will be the north, that will be the south. So some of them will be in a lower level of energy, some of them will be in a higher level of energy, because you are applying a magnetic field. So I'm going to turn on, I'm going to increase the magnetic field here. And you see that most of those little bar magnets, you can imagine those hydrogen atoms behave like a bar magnet. They will be aligned with the magnetic field, okay? Because they want to be at the lowest level of energy. Is that clear? So if I am sitting in an MRI machine, they turn on the magnetic field. So let's say it's going from the top to the bottom. All those little hydrogen nuclei will align with the magnetic field. But because probability is involved, okay, we are talking about quantum chemistry or quantum physics, some of them like to be excited, you know, they don't want to leave their excitement, but most of them will not be excited and will be aligned with the magnetic field. Is that clear? So what you do, you're going to start sending a radio wave. So and if that radio wave, okay, I'm cheating here, but if that radio wave try to excite those nuclei, nothing happens. But if you have exactly the right frequency here, you're gonna excite, okay? You're gonna bring those nuclei to a higher level of energy. So now they are excited. So it means if, again, the magnetic field is going from the bottom to the top, all those nuclei from hydrogen, okay, they want to align with the magnetic field. Now you excite them with radio pulses, so they will go to a higher level of energy. They get excited, like electrons can be excited, nuclei can be excited, and then they cannot stay excited. So they're gonna burp out their energy as photons. So when they're gonna relax, okay, so they're gonna go to a lower level of energy, they're gonna burp out uh, radio waves, okay? And those radio waves will highlight the inside of the human body. So you are using, when you are doing an MRI, you are using radio waves to highlight the inside. That's the idea. If you are doing a CAT scan, you are highlighting the inside with X-ray. If you are doing a PET scan, you are highlighting the inside with gamma rays. So MRI, you don't have a lot of resolution, but at least it's not as bad as a CAT scan or a PET scan. So you see here? So now what do we do that? So let's take this guy. I'm going to increase the magnetic field here. So all of them want to try to be aligned. No, where's my electric field here? Okay. So that will be my magnetic field. So you see all those little nuclei want to align themselves with the magnetic field, okay? So they are at a lower level of energy. Now you're going to send a radio wave, like pulses of radio wave, that will excite them and force them to be in a higher level of energy. When they're going to burp out that energy, it will be burping out that energy in the form of radio wave from inside out, and it will highlight whatever is inside. Okay, so let's put a tumor, God forbid, of course, and the tumor here. So tumor, that means you're going to have a lot of hydrogen atom, and we're going to excite it with a radio wave, so a lot of power, and we're going to change the frequency. Ugh. I just have to write to find the right frequency. Ah, here we go. It's very hard to find the right frequency. 7 should be like 70. Here you go. So you see, you're gonna have more radio waves being emitted by the tumor here. So that's how you can know that there is a tumor there. You see how it works? But it works for a given frequency, not for all frequency, okay? So this is called the resonance frequency. Oh, here you go. You see how much you have here? Do you see that? Okay? So again, because of the magnetic field, all those little protons that are spinning, hydrogen proton, align themselves with the magnetic field and they are very happy. And then you excite them, you force them, okay, to go against the magnetic field, so they will be in a higher level of energy. And then once they come back, okay, they're gonna burn out radio waves. Those radio waves go from inside out, and you have what is called tomography. You have a 3D image of whatever is going on inside. But that works only for soft tissues. If you want to look at bones, for example, you have to take a X-ray. CAT scan, you will have better resolution, but you are exposed to X-ray. PET scan, you are using gamma ray, so it's a smaller photon. so smaller, better resolution. The PET scan is you cannot have too many PET scan because it's gamma rays. Is that clear? So it's simplified, but it's important to understand that. Okay, so this is what's happening. Okay, you have a nucleus. Okay, proton. Okay, the proton is spinning, so it's behaving like a bar magnet. It wants to align itself with the magnetic field. You excite it, you force it to twist. Now it's in its excited state. Okay, and once it's coming back, okay, it's go back to the lower level of energy. It's gonna burn out a radio wave in this case. Okay. Okay, so let me ask you something here. So if you have, so first of all, question here, conceptual question, easy, typical for test 3. In which position the nucleus here, hydrogen nucleus will have its lower potential energy or lower state, energy state? Is it A or B? A. Very good, okay? When it aligns itself with the magnetic field, it has its lowest level of energy. You have to do work to force it against the magnetic field. And then it wants to go back. Is that clear? So the highest level of energy will be B and the lowest will be A. Okay? Do you agree? Okay, so what about here? So let's forget about the hydrogen nucleus for now. Now I have a loop of current and it's inside the magnetic field. Is it happy? So you take your right hand rule, okay, the thumb. Imagine that will be your thumb here, okay? That will be your north. Is it happy here or is it in the highest level of energy? Higher level of energy? It's not happy, okay? Do you agree? So which way is going to twist? This way or that way? Which is clockwise or counterclockwise? Huh? It wants to go this way. Do you agree? Let me show you that. See? It's this way, right? The magnetic field is going in that direction, so it wants to rotate to align itself with the magnetic field. So in that case, it will be at its lowest level of energy and it's gonna have to be happy. Is that clear? Okay, again, if you have a bar magnet, if you have a loop of current that will behave like a bar magnet, it wants to align with the magnetic field. So if you have a magnetic field from the left to the right, okay, that could be a compass, it could be a bar magnet, it will be a loop, it will twist to be in this direction, and it will show which way the magnetic field is flowing. Is that clear? Yes.
No, I'm trying to. Yeah.
Okay. Okay. You can show that. Can show that with a force. You see, you have a piece of current here. Okay, you have a magnetic field. The current is going into the screen. The magnetic field is up, so the force will be to the right. Same thing for the segment up. We have a force. Do you remember physics 1 when you have a force in which in this direction and a force in other direction, you get a torque. So there will be a torque. Is that clear? So remember, the physical quantity torque, okay, is a way to measure the twist, how efficient the force are in making the twist happening. Okay, so each time you have a loop of current inside a magnetic field, there will be a twist to make sure that it aligns with the magnetic field. Is that clear? Yes.
The is it the rectangle box or is it the arrow?
No, that's the loop of current, okay? Except it's instead of being a circle, it's a square. So the current is going this way into the screen, that way towards you. So that's why you have those two forces that will be providing the torque. That's one way to look at it. The easiest way to look at it, again, because it's a loop, you take your right hand, okay? You have your thumb here, so it wants to align with the magnetic field. Is that clear? So the current here is going in the screen, out of the screen. So that's why you have those magnetic forces. And when they act together, it's going to make a twist. It's like driving a car. When you are driving a car at the wheel, you apply a force in this direction, apply a force in that direction, so you make the twist happen. Okay, does that answer your question?
Yeah, so when you have you would only be able to tell the current and then just give a
Yeah, so once you know the current, you know the north. And the north, once you have the north, it's like a magnet, so it wants to align with the magnetic field. Is that clear for everyone? Okay, so we can define a new physical quantity. We call that the torque. The torque, remember from physics 1, the unit for torque is Newton meter, and the torque applied to a loop of current inside the magnetic field will be equals to the number of loops times the current times the magnetic field times the area of the loop. So it can be a square, doesn't have to be a loop, times the sine here. The sine will be the angle between this here, perpendicular to the area, and the magnetic field. You don't have to worry about the sine. We'll try to make it, we'll see. Okay, let's take an example here. So which way is the north in that case? So you have a magnetic field, you have a loop. Take your right hand. Where is the north? Where is your thumb? Up. So is it happy to be up? No, it wants to align with the magnetic field. So which way it wants to rotate? This way, right? It means oops. So this way. So this way. So it wants to go south. That way. Yeah. So this is north. Wants to go to south. So it goes here. Go that way. Do you agree with that? Yes. Okay. So that will be clockwise. Right? Is that clear? No. You take your right hand this way. That will be your north. North wants to go to south, so it's going to rotate this way. And this is south, wants to go to north. And then it's going to be happy. And then it will be stuck there. Unless you do something special that we'll talk about. Okay, so let's find the torque. Let's apply the equation here.
why does the south to the right? Why does the
Because this is the current, this is your north. North wants to go to south. And south wants to go to north. That will be for the lower state of energy. If you don't want that way, you will have to do warp. Okay, so let's just apply the equation to find the torque. Remember physics 1, there is a torque applied. The unit is Newton meter, so make sure on the equation sheet you are able to find it. Let's just apply the equation. So the torque will be how efficient is the force, are the forces to apply a twist, right? So there will be a twist, and we need to find the torque. So the torque, the notation is tau. Newton meters are the units. It's going to be the current. Of course, it has to be proportional to the current. It kind of makes sense. The magnetic field, okay? It will be also proportional to the area of the loop. It doesn't have to be circular, to the number of loops. And then here, the sign here, theta, but that's going to be 1. Okay? Why? Because the angle between B and your thumb here is 90 degrees. So you don't have to worry about the angle. Okay, so can you do that? How many loops do we have? Does it say that we have more than one loop? No, right? The number of loops is 1. So plug it in. The current is 0.5 times the magnetic field is 120 mega, means 10 to the 6, times the area. Do you remember what's the area of a rectangle? Width times length, exactly. What's your name already? I know you, but yes, Thomas, yes. Thomas, Nathan, Jesse, Giselle, Joanna. Remind me your name. Area will be 0.08 times 0.06. Do you agree? Okay, so that will be the torque. And we get uh, I,
2.88 times 10 negative.
no, not negative. Why negative? You have 10 to the 6 here. Is that right? Do I make a mistake? Did I make a mistake? What did you find? 3 times 10 to the... I don't want to do it. Do it.
Yeah, you're right.
Right? It's a 10 to the 5th. Did you get that or no? No?
That, yeah, 2.8 times.
2.8 times 10 to the 5th. Okay. Newton meters. Okay? So that's called a torque. So make sure you find the equation in your equation sheet. Torque. Okay, we did that last semester. You can look at your textbook. How do they get that equation? It's from the force here. Okay, the force is I times the length times the magnetic field, and then you multiply the distance to the axis of rotation. So I don't want to go through that, but that at the end, that's what you get. Is that clear? Okay. So what is it that we can build with that? A loop in the magnetic field. Something that spin. Something that we use like in everyday. Every day you have those things. It's called start with a M. Something that spin when you apply electricity to it. A motor, right? You have it like in a fan. In your laptop, you have a fan to call it out, and it's because you have a motor. So what's happening here? Take your right hand again. So do you see the current is spinning over there? So where is the knob of the loop? It's inside the screen or towards you? It's inside the screen, right? In the screen. Do you see that? Ay, ay, ay. the loop is this way, okay? So the thumb is in the screen, right? So which way you want to go? That will be up. So it's gonna be spin in this direction. Okay? So it will align itself with the magnetic field. If you don't do something about that, it will get stuck here. But because at that point it's going to lose connection, okay, it will keep spinning because of inertia. So that's what I want to show you. See, I killed my battery on Tuesday. It's dead. So if you want to bring that home as a trophy, you can. You can work out if you want. Okay, so you have a huge magnet. Thank you. And here, what's that letter? No. Okay, so do you agree the magnetic field is going in this direction? Yes? Okay. What is that? It's a loop. Okay, it's a loop of current. I don't have current yet, but I will connect it. So you will have current here flowing. And if current is flowing, what's going to happen? If the current is flowing this direction, okay, it will rotate to align itself with the magnetic field from here, right? Because then you will have south attracted to north, right? So it's going to spin, and then here it wants to stop, but because I'm going to lose the connection, it will keep spinning. And we have a motor. So if you want to build a motor, you get extra credit. Better is your demo, more extra credit you get. So if it's a baby extra credit, you get baby extra, a baby demo, you get baby extra credit. Do you think it's gonna work? Yeah. You see that? So it's the magnetic field interacting with the magnetic field from the loop. Okay, isn't that cool? I don't know if you can see. Isn't that cool? Right? So again, what's going on? Once you have current flowing here, it will rotate in such a way to align itself with the magnetic field. But at that point, instead of being stuck, there is a secret here, a little secret, that this wire is only partially sent out. Okay, so at some point it will lose connection because I have some varnish here, so it will keep spinning. So that's the secret behind the motor. So it's a DC motor. I have a small one here, but inside, I don't know if you can see, but you have 3 coils here. Can you see the 3 coils? So each one will interact with the permanent magnetic field. So it's going to be pushed by one, pushed by the other one, pushed by the other one. So it's supposed to spin faster. Okay, so let's see if it works. Same idea. And now here is an idea for extra credit. Sometimes it's working, so you can find You can find tutorials on YouTube. But it's the same idea. You need neodymium magnet. It's a very strong magnet. And then you magnetize your battery. Yeah. And then you have a wire like this. Keep going. So let's try. Maybe this one will work. This one is going. Isn't that crazy? So you need three things. You have electricity flowing, okay? That's from the battery. Um, so you have your wire, and then you have your magnetic field. So as long as you have a magnetic field and a wire, there will be a force acting on the wire, and you can have this. That was done by a student last semester. I can show you why. So I have so many wires. I'm totally confused here. I don't know. Ah. Let's see. So I just want to show you how it works. Mm. So you have magnetic field going in this direction. You're going to have the wire going in that direction. And you have the magnetic force here. Don't see very well. Is there a video? Do you see? It's called a homopolar motor. Okay, here. So you can look up online. Okay, so the idea is that you have electricity flowing in this direction. You have a magnetic field flowing in that direction. So you're going to have a torque applied. So that's one thing you can do. So it's called homopolar motor. You have other video like this one. I used to do that with kids. So it's the same idea, right? You have a loop of current. You have a permanent magnetic field. You have current flowing, okay? So the loop wants to be stuck. But because one side here is partially insulated, so some of it is not insulated, that means it will not be stuck. It will lose connection and keep spinning. So it's not that hard to make, but you need like wires with some kind of insulation. It's called enamel wire, and you need a sandpaper. So it's very cool. You have many tutorials for that. Let's see, motor. Let's see if I have another video.
is basically a current loop that's placed in a magnetic
Okay, so here you have the explanation.
field, typically between the poles of a permanent magnet or maybe an electromagnet, so we can do it either way. And that loop rotates. It's on some kind of bearings on a shaft. And here's the really clever thing. Toward the left there, you see a battery connected to this structure. But of course, the battery's stationary and this loop is rotating, so we somehow got to get the current in there. So we have these little semicircular rotating copper or other metal pieces, and we have things called brushes, which are typically made of wire or carbon, and they're contacting those rotating surfaces, and they're letting electricity flow through. And here's the really clever thing. That connection is called the commutator, and you see a little gap there in the commutator. And what happens is, as the loop rotates, it would normally just align itself with the
So it wants to stay here, right? But because it's losing contact, there is no more electricity flowing, so there is no more force, so it will keep spinning because of inertia. So constantly, the permanent magnetic field here is interacting with the magnetic field from the loop. So it's constantly pushing it.
magnetic field, as we've just seen. But just as it gets near alignment, that commutator switches past that gap, and that reverses which part of the battery is connected to which part of the loop, and that reverses the direction of the current in the loop, and that means the loop is no longer in alignment with the field. In fact, it's out of alignment, and it wants to rotate a whole 180 degrees to get back into alignment, and so it tries to do so, but just as it barely gets there, the commutator reverses the direction of the current again.
So that's one way to do it. So these are electric motors. Okay, so again, you need a loop of current, you need a magnetic field, and you will have a torque applied. At some point, the contact will be lost, okay, so it will keep spinning. A lot of application, that's where the very old galvanometer were to measure the current. You see inside those machines here, you have a loop. You can see the loop here, and it will be twisted. Okay, and the amount of twist will be proportional to the current, so you can calibrate it to measure the current. Okay, so let's try to do this one. Okay, so you do it. So it's one loop. Okay, so what's the torque? It's the number of loop times I times B. What else? Times the area times the angle between the thumb here and the magnetic field. But in that case, we suppose it's going to be 1. Okay? So number of loops, it doesn't say. So I suppose it's 1 times the current is 5 times the magnetic field is 30 millitesla. So that's going to be 10 to the negative 3 times the area. Area is width times length. So it's going to be 0.1 times 0.2. So that's going to be, okay, 0.003, which is a negative 3, no? Did I make a mistake? Good. So 0.003 Newton meters. Okay? If you don't stop the current from flowing, it will get stuck. Do you agree with that? If you don't do anything, okay, the current is flowing this way, it will stay stuck here, right? It will align with the magnetic field. But what they do, they stop the current from flowing. So there is a trick for that. The current stops flowing, so it keeps spinning, and again you have a torque applied. Okay, so let's try to do this one. So the magnetic moment, the definition for magnetic moment is just the current times, I will give you the definition, that will be easier. So what's the magnetic moment of a coil? Okay, it's a physical quantity, mu, and it's going to be equals to the number of loops times the area times the current. Okay, and the torque equals the number of loop times the area times the current times B. Okay, if the angle is 90 degrees, and this is called mu. Okay, so mu is called the magnetic moment of the coil. So unit is amp. This is the area. This is amp times meter square. Okay, you don't have to worry about that. Okay, you want to have this. Okay, let's stick to this. The torque will be the number of loop times the area times the current times B times the sine theta. And this is 1. Okay, so you have 100. The area is given, so it's going to be 2 times 10 to the negative 4 times the current is going to be 0.045 times B is 0.15 times 1. 1.4, yeah, Newton meters. Did you all find that? Right? Now, what do we call the physical quantity named the magnetic moment is just this quantity here. This is called the magnetic moment. Okay, so if I don't know if it's in the MCAT or whatever, but that physical quantity is the name for the magnetic moment. Not in this class. So any question? Is that clear? Yeah. Now this slide come again, Johnson and Cutnell, the book that I do recommend. You see that's called the magnetic moment. Okay, we don't have to worry about that. That will be the torque. So each time you have a loop of current inside the magnetic field, it will twist to align itself with the magnetic field. And if all of a sudden you stop the current, okay, it will keep spinning. That's how you have an electric motor. So you have electric motor everywhere. Okay. Even in the computer you have them. The Prius you have them. It could be industrial. And each time you're gonna have a coil, okay, like a solenoid. So current loop. Okay, any question? So what do you think? Let's go back to if where is my slide here? So if you have wire inside a magnetic field, so a wire with a current flowing through it inside the magnetic field, it will be acted upon by a force. Turns out that you're going to have the same thing if instead you have a moving charge. So if you have a moving charge inside a magnetic field, the moving charge will be acted upon by a force, okay? And that will be QVB. So that will be the velocity here. That will be the magnetic field, and that will be the force, okay? So we're going to see a lot of applications, including the mass spectrometer that you're going to use in biology, okay? So if you have a moving positive charge inside a magnetic field, the charge will be acted upon by a force, and you still use your right hand. So if this is the moving charge, if this is the magnetic field, the force will be perpendicular to both. If the angle is 0, what's going to happen to the magnetic force? It's going to be 0, because sine of 0 is 0. If the charge is not moving, you have a positive charge inside a magnetic field, but it's not moving. What's going to happen to the force? 0, very good, because the velocity is 0. So understand the difference with an electric field. If you have a positive charge inside an electric field, can the electric field exert a force on the charge even though it's not moving? Yes, F equals QE. The charge will accelerate. However, for a magnetic field, okay, to exert a force, the charge has to be moving. Only moving charge will experience a magnetic force. If it's at rest, it cannot experience a magnetic force. And the angle cannot be 0 and cannot be 180. So you can show that with a cathode ray tube. So inside the cathode ray tube, what is that beam? What is it made of? Do you remember? It's a beam of electrons. It's a beam of electrons, right? So here you have a negative electrode. Here it's going to be positive. So this is the cathode, this is the anode. Here it gets very hot. Okay, the electrons break free. So what's going to happen to them? They're going to accelerate toward the plus, right? So because the magnetic field, let's review, where is the magnetic field? This is plus, this is minus. Electric field will be from plus to the minus. So the electron wants to go against the electric field and they will accelerate. Now, if I have a magnet, you see the magnet will deflect the electrons because it's a moving, electrons are moving charges. Okay, you can show that time you are very late. Is that traffic or what? You just the bus.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Isn't that cool?
Here we can see the electrons being deflected by the magnet.
Isn't so cool? Right? You see, a magnet or magnetic field can deflect moving charges, right? A beam of electrons can be deflected. except if you want to know which way it's going to be deflected, you can take your right hand, okay? But then the force will be the opposite. Or if you want to find the force, you can take your left hand. So right hand is for positive charge, left hand is for negative charge. Or you can say the positive charge, and then if you are not afraid, if you have very flexible bone, okay, once you find the force, if it's an electron, you do this. Oh, look at that, I have flexible bone. I hope I'm not losing bone density, because look what I can do. Can you do this? Ah, you can't, right? So maybe I have to worry about it.
Cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
And that's a way to destroy those old TV. You see, the old TV were cathode tube, and if you take a magnet here, we can interact with the path of the electron, and usually you do damage that will stay. Okay, so so what do you think here? If there is zero magnetic field, okay, magnetic force, if the particle is neutral, can you have a magnetic force? No, very good, because you need to have a charge, positive or negative. If the particle is at rest, not moving, can you have a magnetic force? No, because you need to have a velocity. If the particle is moving along the magnetic field, so if they are both parallel, so the angle is 0, can you have a magnetic force? No. Do you see all the question I can have for test 3 conceptual question is they are very cool conceptual question. If they are anti-parallel, so if the magnetic is going this way and the particle is moving that way, can you have a magnetic force? No, because sine 180 is 0. So that means all of them are possible. Okay? So let's try to do this one. So you have a moving charge here. Proton. So proton are what? Positive or negative? Positive. So let's take your right hand. So so it's a VBF. VBF. So the particle is moving to the right. The magnetic field is up. So the force is towards you. Very good. Towards you. What about this one? You just reverse the velocity. So the force will be away from you. Do you agree? The velocity is to this way. Magnetic field is this way. So the force is in the screen. Yes? Do you agree? What about this one? Is there a force here? No force. So let's just compute the magnitude of the force for number 1. So what did we say? The force is towards you. I'm going to make a dot. Okay, so the magnetic force equals Q, V is velocity, B, okay? And it's the sine between V and B. So that's the angle between V and B, but that's going to be 1 because the angle is 90 degrees. So that's your little proton here. And that will be the velocity here, and that will be the magnetic field. So do you remember the charge of a proton? 1.6 times 10 to the negative 19, okay, times the velocity, which is 2 mega, so 10 to the 6, and the magnetic field is 0.1. Okay, so what you get? 2 point what?
No, 3.2 times 10 to the negative 14.
Thank you. Did you get that? Okay, so that will be force number 1.
Is it for the charge? We don't multiply it by 3, it's just use 3 and split it.
Yes, no, it goes for each case. What's going to be the force in this case? What's going to be the force in this case? What will be the force in that case? Okay, so the answer is 3.2 times 10 to the negative 14. Do you agree? In that case, the force will be the same in magnitude. Do you agree? For number 3. Okay, except it will be in the screen. So here you have a force in the screen, and then you have a force towards you. And what's going to be the force here? 0. There is no force. Okay? And then we want to do, I see that everyone is tired. Let's see. By the way, the way you have cookies, okay? I don't want to take them home. Come on. I'm trying to launch. Open. Oh. Okay, so I'm going to remove the electric field. Okay, so you have a moving charge here and it's positive. And the magnetic field is which way? In the screen or towards you? In the screen. So the force will be where? So the particle is moving this way. The magnetic field is in the screen. So the force will be up. But you see that the force is perpendicular to the velocity. When the force is perpendicular to the velocity, it means that the object will describe a circle because it's a centripetal force. Let's see. It's a circle, but we're gonna make it go faster. Bear with me. Don't go anywhere. Okay. We're gonna make the magnetic field a little bit weaker. Okay. Let's see. That's what it does. If you have a moving charge inside a magnetic field, the charge will circle out, okay, around the magnetic field. Okay, so why is that? Because let's see if I have time. 2 minutes, I have 2 minutes. Do you remember when we had the Earth here? And you have the moon? And the moon wants to keep going in a straight line at a constant speed. Can that is possible? It wants to keep going straight at a constant speed? No, it can't, because there is a force here pulling back on the track. Okay, that force here is perpendicular to the velocity. So this is called a centripetal force. So each time you have a force perpendicular to the velocity, it will describe a circular path. Okay, so if something is moving in this direction and there is a force in that direction, okay, it will start to circle around. Okay,